Welcome to another Mathologer video. Today's video is about the absolutely wonderful wobbly table theorem. Some of you may already be familiar with a very pretty special case of this theorem, which became quite well known a few years ago when Numberphile dedicated a nice video to it. This special case of the theorem runs as follows. Take a squared table like the one over there. At the moment, this table is hovering above the floor. A bit unusual behavior for a table, but perhaps it's due to the ghostly presence at our séance. Anyway, the feet of our spooky table are blue, and the points directly below the 4 feet are marked in green. The ghost then disappears and the table plonks onto the surface. Chances are that it will wobble, right? Not because the ghost is still playing games, but just because the floor is uneven. How do we stabilize a table? Well, usually people will wedge a napkin or whatever under one of the wobbling feet, like this. However, the wobbly table theorem says there's another method. The theorem says that if the floor is not too crazily uneven, then you can stabilize the square table simply by rotating the table on the spot, like in this example. So just rotate it and eventually all 4 feet will be touching the ground. Super neat, isn't it? And this actually works very well in practice. Try it on your next cafe trip, for example. And this is only a small piece of some nice and mostly unknown table turning maths, which also applies to non-square tables. Well, let's see. Now, before we get going, I have to make 2 very important disclaimers. First, when I'm talking about a square table, I always mean that the feet of the table form a square. Of course, that's not always true, even if the table surface is square. Often enough, real-life wobbling is not caused by the uneven floor, but by the table having feet of unequal lengths. For example, over there, we've got a table on a nice flat surface, but one of the legs has been gnawed at by a beaver or a ghost or whatever. Anyway, one leg is shorter. So even though the table is standing on a flat ground, obviously there's no way of shifting the table around to make it stable. Well, we could turn it over with its legs in the air, but that would be cheating. So again, by a square table we mean the feet of the table form a square. Second disclaimer. By having stabilized the table, we do not mean that the tabletop is necessarily horizontal. Usually, the stabilized table will still slope in some manner consistent with the uneven floor. Of course, such a slope can also be annoying, but definitely not as annoying as a wobble. And typically, in real life, a slight unevenness in the ground will translate into a slight and not too annoying slope of the tabletop. With those 2 disclaimers stored away, it's time to have some serious fun turning the tables. Now, to do that, we'll start with Homer Simpson. Of course, it's never the wrong time to introduce some Simpsons into the discussion. Recall that my last video was all about Fourier series and how to draw complicated pictures like this Homer drawing with epicycles. I'll announce the winner of the epicycle competition at the end of this video. For now, let me recycle Homer as a warm-up exercise for our table turning. Let's begin by framing Homer in a rectangle like this. I call this sort of rectangle a hugging rectangle because Homer touches all 4 sides of the rectangle. Of course, there are infinitely many hugging rectangles, one for each possible orientation. Here are a few more. There's one, and there's another one, and one more. Now, the aspect ratios of Homer's hugging rectangles will vary, but it turns out that one of them is special. One of the hugging rectangles is a perfect square. And that was not luck. It turns out that any picture will have a hugging square. Not obvious at all, but it's true. We'll give the idea of a proof in a minute, but first, here are a couple more examples to illustrate. Apple, 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 and here is its square. Linux penguin, and here's its square. Fish, square. Just a few random points, square. Now, it can happen that a shape has more than one hugging square. For example, all hugging rectangles of circles are squares. Question for you. Are there any other shapes all of whose hugging rectangles are squares? Leave your answers in the comments. Here's a hint. Take a close look at the Mathologer homepage. Okay, here's the gist of a proof that every picture has a hugging square. We start with any hugging rectangle, as in the example over there, and color pairs of opposite sides, red and blue. Now let's rotate this rectangle through an angle of 90 degrees, so that at every stage we have a hugging rectangle. All right? The key observation is that the dimensions of the hugging rectangle will change slowly as we rotate, with no sudden jumps. Using maths jargon, we would say that the dimensions change continuously as we rotate. Now, having rotated through 90 degrees, we're back where we started, with the same hugging rectangle. Let's double check. Yeah, exactly the same, right? Well, not quite. Have a closer look. What has happened is that the red and blue sides have swapped places. That may not seem important, but it's the key to capturing our hugging square. Okay, back to the beginning. 0 degrees. Let's record the difference between the red and blue lengths as we rotate. To begin, red is longer than blue, so the starting difference will be what? Positive, negative, or 0? Well, positive, of course. However, because of the swapping, at the end of the 90-degree turn, red will be shorter than blue, and so the difference will be negative. Now, since the hugging rectangle changes continuously, this implies that the difference, red minus blue, will also change continuously, from positive to negative. And this means that at some point the difference has to be 0. But the difference being 0 means that red is equal to blue, that the red sides are just as long as the blue sides. And of course, that means that at this instant we have a hugging square. And that works for any picture whatsoever, not just Homer. Super neat, isn't it? Just start with any hugging rectangle, start rotating, and you're guaranteed to come across a hugging square. What has all this to do with table turning? Well, a very similar above than below argument shows why, as you turn your wobbling square table through 90 degrees, you can expect to come across a stable position, with all 4 feet touching the ground. Okay, mathematical seatbelts on? Then here we go. Say that square table is on the ground and it's wobbling, with the 2 blue feet touching the ground and the red feet moving up and down as the table is rocking back and forth. Now wobble the table so that the 2 red feet are exactly the same vertical distance from the ground. We'll call that an equal hovering position. Now let's rotate the table 90 degrees, always with the 2 feet in the air in an equal hovering position. Here we go. Okay, how have we ended up? Well, the table is exactly in its starting position, except red and blue have swapped. Now it's the red feet on the ground with the blue feet hovering. But obviously the swapping is only possible at an instant where both the blue feet and the red feet are on the ground. We can also graph this as we did for the hugging rectangles. Let's do that. Here, red and blue stand for the vertical distances of the red and blue feet from the ground. Then, just as before, this difference function starts out positive and ends up negative, and so should be exactly 0 at some instant along the way. As earlier, we conclude that both red and blue are the same at this point. However, since at least one of red and blue is 0 at all times, at this special pink zeroing time, both the red and blue distances must be 0. This means that all 4 feet are touching the ground and our table has been stabilized. Fantastic. Okay, so a square table can always be balanced by rotating it. Always? Really? Well, let's put it like this. I've been using this trick for decades to stabilize real-life tables, and it's never failed me. On the other hand, it's quite easy to conjure up scenarios in which different parts of our argument break down and/or stabilizing by rotating won't work. Second challenge for you today: try to come up with some setups that foil our argument. Just to get things going, here's something very simple. When we lower the table over there its top will hit the top of the mountain and the feet will never reach the ground. Duh. Now that we have the square table sorted, give or take some finicky details, let me tell you a little bit about the history of mathematical table balancing, the broader scope of the nifty unwobbling by turning argument, and the part my friends and I played in turning this intuitive argument in a nailed-down mathematical theorem. Okay, hands up. Who knows this guy? Marty's hand is up. Well, out there in YouTube land, not many people are nodding their heads. Marty, this is terrible. Our hero has been forgotten. This is Martin Gardner, by far the greatest popularizer of mathematics of all time. Starting in the 1950s and for a quarter of a century, Gardner wrote the hugely influential Mathematical Games column in Scientific American. He's also the author of more than 100 books on popular mathematics, magic tricks, and so on. Gardner inspired more people of my generation to become mathematicians than anybody else. For example, you can only watch this video because I really got into maths as a result of reading Gardner's books. And if you enjoy Mathologer videos, it's mostly because of the lessons I've learned from Martin Gardner. He was a master at explaining real mathematics as simply as possible and no simpler. In fact, much of popular mathematics in books or on YouTube or wherever have their origin in a Martin Gardner column. Hexaflexagons, Conway's Game of Life, Dragon Fractals, public key cryptography, wobbly tables. Yes, table turning. In the May 1973 issue of his Mathematical Games column, Gardner challenged his readers to discover a version of our heuristic argument for why stabilizing a square table by turning should work. He then supplied an answer to his puzzle in his next column. Gardner credits Miodrag Novakovic and Ken Austin as his source for the wobbly table trick. I actually tracked down Ken Austin about 15 years ago, and he told me that in fact it was his friend Miodrag who discovered the trick and how to justify it around 1950. Ken only communicated the trick to Martin Gardner. Miodrag's version of the table turning is actually a bit different from the one I showed you, and is also well worth checking out. Yet another version of the argument is presented by the prominent German mathematician Matthias Craig, who is the star of Numberphile's 2014 table turning video. Also definitely check out that one. Now for a surprising twist. Have a look at the last sentence of Martin Gardner's write-up. A similar argument can be applied to wobbly rectangular tables by giving them 180-degree rotations. Now, of course, that's very welcome news, since out in the wild, most tables are rectangular, but not square in shape. And there are lots of other objects whose feet form rectangles, to which all this applies. For example, I personally use stabilizing by rotating quite often with my trusty step ladder. Anyway, why does everybody only go on about square tables, if this all works much more generally for rectangular tables? Well, when you try to adapt the slick argument for square tables to general rectangular tables, you'll find that this is not nearly as straightforward as Gardner's off-the-cuff comment suggests. Now, before I show you how to extend the argument to rectangles, let me tell you about the almost definitive paper on wobbly tables, which a couple of friends and I published in 2007 in the Mathematical Intelligencer. There, Marty is also taking a bow. This paper was all about making the wobbly table argument into a nailed-down mathematical theorem by hammering out on which surfaces a perfect rectangular table can be stabilized by turning it on the spot. One of the main results of our paper is that stabilizing by turning is guaranteed to work if the ground and the table have the following properties. First, the ground. The ground has to be Lipschitz continuous with associated angle of at most 35.26 degrees. Whoa, that sounds scary, but it's not really that bad. All it means is that the ground is given by a continuous function, and that between any 2 points on the ground slopes at an angle of at most 35.26 degrees. Another way of putting this is to say that when you slide around the coney 3D counterpart of the green wedge, all of the ground will always be below the wedge. So the scary term Lipschitz continuous amounts to a maximum slope requirement for our ground. Okay, so ground continuous and not too steep, check. And what about the table? Well, obviously, in line with our introductory disclaimer, the feet should form a rectangle. And we also require a minimum leg length. If the legs are at least half as long as the diagonals of the tabletop, then nothing can go wrong in the way of little hills bumping into the tabletop. So what Bill, Marty, Rainer and I prove in our paper is that as long as the surface is continuous and not too slopy, and as long as the table legs are sufficiently long, a perfect rectangular table can be stabilized by turning. The heart of this theorem is the extension of the nice heuristic argument for square tables. But to be able to use this argument, we had to do some pretty hard work to make sure that our conditions guarantee that the table always rotates as nicely as suggested by the animations that I showed you earlier. The idea underlying the proof and many similar proofs is the so-called intermediate value theorem. This is a mathematically rigorous version of the intuitively obvious fact captured by our positive to negative diagram. The fact that if a continuous function changes from positive to negative, it will be zero somewhere along the way. In fact, in the proof, we use the intermediate value theorem not just once, but about a zillion times. And for those of you keen on the gory details of the tricky proof and some of the other nice results in our paper, I'll provide a link in the description. Now, before we look at the proof for rectangular tables, here's an interesting open problem. Is there any non-rectangular four-legged table which can always be stabilized by turning? For example, what about the half hexagon table here? So, is it possible to stabilize this or some other mutant table by rotating? Let me just tell you about one neat observation. It turns out that it is important whether or not the feet of a table lie on a circle. Well, that's true for our half hexagon table, and of course it's also true for all rectangular tables. Why is the circle business important? Well, it turns out that if the feet of a table are not on a circle, then there is definitely a not too slopy surface on which this table will always wobble. Last challenge for you today. Prove this non-concircular feet implies doomed to wobble theorem. Okay, now for the hardcore Mathologer fans, let me sketch how our simple heuristic rotation argument for stabilizing square tables can be extended to rectangular tables. Okay, deep breath. As with square tables, we'll rotate rectangular tables such that at all times they are at an equal hovering position. So at all times throughout the rotation, either the blue pair of feet is on the ground with the red feet hovering an equal distance above the ground, as pictured over there, or vice versa. So if we can show that at some instant during our rotation we are guaranteed to have the blue feet on the ground, and there's some other instant where we're sure the red feet are on the ground, then we can argue with continuity as before that somewhere in between all 4 feet have to be on the ground. Now, an obvious difference between the square and rectangular cases is that a 90-degree turn won't work. For a general rectangular table, we have to rotate 180 degrees to bring it back to the starting position. But now the problem is that after a 180-degree turn, the same pair of feet are on the ground as at the start. Let's have a look. There, turn, same feet on the ground. So unlike in the square case, the end position after the half turn is not distinguished in any way from the starting position. So our rotation in this case doesn't automatically provide us with that second crucial position, where the 2 feet that were hovering at the start end up on the ground. Instead, I'll show you that the crucial position always exists using a proof by contradiction. So, let's assume that the opposite of what we want to show is true. Let's assume that somewhere in the universe there's a rectangular table and a surface for which the table cannot be stabilized by turning. We're in Fantasyland now, and so to keep things as uncluttered as possible, I'll only show you the table and the underlying green points on the ground. Now, if this table cannot be stabilized by turning, then the blue feet must stay on the ground throughout the rotation, and the red feet will be hovering in the air all the time, something like that. Right? Blue feet on the ground and red feet hovering all the time. Let me now show how this assumption leads to a contradiction, which then finishes the proof, modulo all the finicky details contained in our Intelligencer paper. Let's highlight the rectangle formed by the feet, and let's also highlight the z-axis around which we are rotating. That brown line is the z-axis. And let's get rid of the non-essential bits. Now, we'll make sure that the center of the rectangle will be on the z-axis throughout the rotation, like that. So the center just wanders up and down the z-axis as we turn. Okay, two important observations. First, since we are rotating through 180 degrees, you've just seen all possible balancing positions of our table with the center on the z-axis. There are no other balancing positions like this. Second, let's call the height of the center of the table in a certain position the elevation of the table in this position. Now, as we rotate, there will be a position of the table where the elevation is at a minimum. Let's see. Okay, so it's wandering. Now, where's the minimum here? Okay, did you spot it? Well, there it is. We're almost ready for the punchline. Notice that if the diagonal connecting the red points is translated straight down, the diagonal will connect the green dots underneath. But this means that we can rotate the table into a new balancing position with the blue feet ending up at those two green points. But this new balancing position is absolutely impossible. Why? Because the elevation of the new balancing position is lower than the supposedly minimal elevation that we started with. And that's the contradiction. Pretty tricky, but also pretty cool, don't you think? And that's it for today as far as table turning is concerned. I've just got one more thing to do before I sign off, announce the winner of our epicycle competition from last time. Lots of nice ideas and implementations which I've listed in my comment pinned to the top of the epicycle video comment section. The one I settled for as the winner is by Tetrahedry, who succeeded in doing something extra special. Their epicycle system simultaneously draws out 3 iterations of a space-filling curve. How neat is that? Check out the details of how they did it in the description of their video. Okay, Tetrahedry, please send me your contact details via comment and I'll send you Marty's and my book. And thanks again to everybody who took part in this competition. And that's it for today. Happy table turning.